In this video, we will discuss the method of reduction of order. The question motivating us is if we have one solution we know of a second order homogeneous differential equation, can we find that second linearly independent solution that we require to form a general solution? And reduction of order allows us to do that. So note we need two things: a solution that is not zero to start with, and then secondly, we need to have that differential equation in this standard form. That is, we need to have a coefficient of 1 for the y double prime term. In that case, the second linearly independent solution we are looking for, let's call it y2, is given by y1 multiplied by the integral of e to the minus integral p of x, and this is all divided by the quantity y1 squared. And looking at this formula written in general, it certainly looks difficult or maybe involved, but remember, for any concrete example, you will know precisely what function you have for y1 along with p of x. Once again, make sure you're in standard form, and once you are, p of x is the coefficient of y prime. Now for a common example. Given that y1 equals x to the fourth is one solution for this second order homogeneous differential equation, let's go ahead and find the general solution on the interval from 0 to infinity. And in order to find that general solution, what we need is a second linearly independent solution. So immediately this is a problem that requires reduction of order. The first thing I'm going to note is we need to get this in standard form. The leading coefficient here, x squared, is most certainly not 1. So we divide everything by x squared. So equivalently, this differential equation would be y double prime minus 7 over xy prime plus 16 over x squared y equals 0. Now we are in standard form, and then p of x would be that coefficient of y prime. That would include the negative sign with the 7x. And with that in mind, our second linearly independent solution is going to be y1 multiplied by the integral of e to the minus integral of p of x, all divided by y1 squared. So that would be x to the 8th. And almost immediately, I'll just go ahead and evaluate this integral that plays the role of our numerator to the side. So those negative signs cancel off, and what we have left is a very familiar looking integral and a very familiar simplification. So that constant becomes a power inside the natural log. Once it does so, we can cancel, and this simplifies to being just x to the 7th. And I'll just put a small note here, since we're looking for an interval on a solution on the interval from 0 to infinity, I just went ahead and dropped those absolute values. And this gives us something much simpler looking to the left. Substituting that in, this now looks a whole lot better. So we would have x to the fourth times the antiderivative of 1 over x, and now this is something we can handle quite easily. So it did look difficult at first, but once we take care of that integral, substitute in the specific function, it should be something that we're able to work with. And remember, when you are using reduction of order, this is one of those scenarios where we do not need an additional constant. What we are guaranteed by the method of reduction of order is that this function y2, it must be a second linearly independent solution. And that immediately tells us what the general solution will be. It's made up by being c1 times y1 plus c2 times y2. And let me just finish by noting the question can be phrased in multiple other ways. Instead of saying find the general solution, we could simply state find a second linearly independent solution. Or equivalently, we could just ask you to find a fundamental set of solutions. the work for all three of those variations on the question is identical. It's the conclusion that changes a bit.